Heap. What is a heap? A heap is a complete binary tree that satisfies the heap property. So there are two things here. First thing is that it should be a complete binary tree, and the second thing is that it should satisfy the heap property. So what is a complete binary tree here? A complete binary tree is a tree in which all levels are completely filled except possibly the last level, which should be filled from left to right. So if you have a tree like this, we already learned about complete binary trees. This is a complete binary tree because all levels are completely filled except the last level, which is filled from left to right, right? See, if last level is also completely filled, well and good. But if it is not completely filled, then it should be filled from left to right. That is, this is not a complete binary tree because in the left side, you didn't fill, you just fill the right side. If you are having lesser number of nodes in the last level, those nodes in the leftmost positions. So then this is a complete binary tree. So this is the complete binary tree property. What about the heap property? Heap property says that the key at a parent node should always be greater than all the children. So it can also be the other way around. That is, the key at the parent node can be lesser than the children. But whatever be the condition, you should follow that particular condition throughout the tree. Then you call it a heap. It can either be lesser than or greater than. Okay. So we'll take an example to understand. Let us say this is having value 80, then this is 74, this is 32, this is 63, this is 50. We have two more nodes. This may be 15 and this is 21. This is a heap because one, it is a complete binary tree. The property is satisfied. And the second thing is heap property. Heap property says the key at any parent node should always be larger than the keys at its children. So if you take this parent node, the value is 80. 80 is larger than the value at both its children, 74 and 32. So this node is satisfying heap property. So heap property has to be satisfied by all the nodes. So check for the second node. 74 is larger than 63, larger than 50. So again, heap property is satisfied. What about this node? 32, it is larger than 15, larger than 21. So again, heap property is satisfied. For all the leaves, by default it is satisfied because leaves do not have any children. So there are two types of heaps. One is a max heap and the other is min heap. So whatever we already explained here, this is a max heap. That is, when all the values at parent nodes are larger than the values at children, then you call it a max heap. And when the value at parent node is lesser than that of children, you call it a min heap. So what I'll do, I'll construct a min heap with the same values so that you understand the difference between min heap and a max heap. So if the values are, I'll take 15 on top. Then 15 can have two children, maybe 50 and 21. Then these two should be larger than 50. So it can be 63, it can be 74. Here these two should be larger than 21. So the remaining ones are 32, 80. So this is a min heap. And whatever we've drawn here, this is a max heap. So the difference is clear. That is, in min heap, if you take any node, this is a parent node. If you see both the children, they are both having values larger than the parent. So parent is always minimum in a min heap. Parent is always maximum in a max heap. If you take this node, both its children are having larger values. Again, if you take this node, both its children are having larger values. So this is a min heap. So the condition can either be the greater than condition or be the less than condition. But whatever be the condition, that should be followed throughout the tree. That is when it is called a heap. So there are two heaps. One is max heap and the other one is min heap. So both of these are very useful in many applications. So we'll see that. The next thing is, how will you represent this heap? You know you have this heap. What representation are you going to use? Are you going to use array representation? Are you going to use linked list representation? How exactly will you represent? So for heaps, commonly you always go for the array representation. And there is a reason. The reason is, what is the drawback of the array representation? Drawback of array representation is that if there are empty positions in the tree, all those values will have to be kept empty in the array, because in the array you want to leave a position for each possible node in the tree in the array representation. And because of that, if some node is not present in the tree, here we are only considering binary trees and binary heaps. So if some node is not present, you have to leave space for those nodes in the array representation. This is the drawback of array representation. But the advantage in case of heap is that heap we know is a complete binary tree. And in a complete binary tree, you won't have missing nodes because all the levels will be completely filled. And only level which is not completely filled is the last level. And that also is filled from left to right, which means in array representation, all the positions that are to be represented will already be occupied. So I'll just show you by converting it to array representation. The same heap I'm going to represent using array. So these are my array values. 80. I'll just write them in order. 80, 74, 32, 63. Then I have 50, 15 and 21. These are the values. What did I do? I wrote in level order. Okay. Next thing is I'm going to give indices 0, 1, 2, 3, 4, 5, 6. So there are total of 7 nodes indexed from 0 to 6. The speciality here is I can easily identify which is the child, which is the parent, and so on. I can exactly identify what is the left child, what is the right child, what is the parent, all these directly from array indices. And how do I do that? The idea is very simple. If I want to find parent, of any node, I simply have to do the floor of I minus 1 divided by 2. If I take floor of I minus 1 divided by 2, I'll get the parent. So let us just try this. If I want to find parent of 63, what will I do? I'll take index, which is 3. What is I minus 1 by 2? Given I is equal to 3. 3 minus 1 by 2. So 3 minus 1 is 2. 2 by 2 is 1. Floor of 1 is 1. So the parent of 63 should be at index 1, which is index 1 is 74. Now look into the tree. What is the parent of 63? It is 74. So the formula is right. Take one more. Let us take 15. If you take 15, index is 5. So 5 minus 1 by 2 is 4 by 2, 2. So floor of 2 is 2 only. So what is at index 2? 32. So what is the parent of 15? It is 32. It is right. So let me take some number which will give a odd number. So if I take 4, then 4 minus 1 by 2 will give 3 by 2, which is 1.5. Floor of 1.5 is 1. So if I take index 4, that is value is 50, then its parent should be at 1. So what is at 1? 74. If I take 50, parent is at 74. So the calculation is right. So whichever node you are standing in, if you want to calculate what is the parent, simply do I minus 1 by 2 and take floor. You will get the parent of that node. This is the first thing. Next thing, if you want to find left child. If you want to find the left child, just do 2i plus 1. This will give you left child. And if you want to find the right child, do 2i plus 2. So it's very simple to reach any parent or a child. So let us try these formulas as well. If you take index 2 says 32. So how do you find the left child and right child? Left child is 2 into index is 2. 2 into 2 plus 1, that is 5. And here 2 into 2 plus 2 is 6. Because 2 into 2 is 4, 4 plus 1 is 5, 4 plus 2 is 6. So the formula says left child of 32, that is at index 2, 32 is present. Left child of 32 is at index 5. Right child of 32 is at index 6. So 32 is here. Left child is at index 5, the formula says, which is value 15, which is right. Right child is at index 6, which is value 21, which is here the right child. So the formula is right. So using these formulas, you can directly reach left child, right child, or the parent of any node very easily. So this is why for representing heaps, you always use the array representation of trees, okay? Because it is a complete binary tree. So we know what is heap. It should be complete binary tree, plus it should follow heap property. We understood there is max heap, min heap. We understood how to represent a heap. The next thing is, what are the operations that we are going to do on heap? So we are going to do, one is insert, we want to do delete, then we'll also do peek and heapify. So these operations will be clear when we go to those particular lectures. In insert, we'll just insert a new element into the heap. Delete is for deleting an element of. Peek is for looking at the element. And heapify is in order to build a heap. So this will be clear whenever we go to those lectures. And before we end this lecture, one more thing I have to discuss is, where is heap used? What are the applications of heap? So heap is used in many, one is priority queues. So we'll go to priority queues, we'll understand how in priority queues heap is useful in order to implement it. Then for heap sort, that is a sorting algorithm. For heap sort, we'll be making use of heaps. Then there are many graph algorithms and all where we'll be using. So as we go on with algorithms lectures and all, there will be many applications of heaps. So there it will get more interesting. Once you get very good clarity of heap, then when you're able to make use of heap in order to solve many problems, it will be interesting.